frustration in it, because it's like, you know, it isn't like, oh, here's gravity. Okay, hey, I dropped something and it's going to fall. Okay, great, right? Cool. You see the effects of it, push and pull. That's something you can physically interact with. And so, you know, you take these two pieces of tape, and it was like, okay, well, they're attracted. Okay, well, I mean, there's a couple of ways that that piece of tape could attract the other one. This one could be charged, and this one just could be neutral. So you don't even know if it's attracted, if it's because the other one is necessarily oppositely charged. You could only have one of them that was actually charged, and you bring the other one near it, and it's neutral, and it's still going to get attracted to it. So then it's like, okay, well, how do you define what's positive and what's negative? Okay, well, clearly the balloon was charged, right? So when you all brought the tape up there, and that tape was clearly repelled by one and attracted to the other one, okay, well, that was cool. But then how do you define how the balloon is charged? You know, it's like, okay, great, it's charged. Is it positively charged or is it negatively charged? Because it isn't like, oh, when it becomes negatively charged, it turns a certain color. So it isn't like an acid-base reaction in chemistry where you could have like an indicator or something like that. You can say, well, it's basic, the phenolphthalein turns purple. It isn't like, oh, the balloon is negatively charged, it's going to turn blue. If it's positively charged, it's going to turn red, which would be cool, don't get me wrong. So then also the other thing about it is to a certain extent it's like a gravitational field. It's like, how can you test that there's a gravitational field? Oh, I dropped something. Okay. Well, then it begins to accelerate. Even though we can't see that gravitational field, we can see the effects of it. Now, relatively speaking, gravity is simple because gravity can only be attractive. Okay, there you go. It just has to be attractive. But the equation that we're going to get into today, where you have F equals K, Q1, Q2 over distance squared, which is going to get you the magnitude of the force between two objects. Here's the problem where this becomes complicated. Number one, this K value is a constant. We'll talk more about that later. But now you have two charged particles. Okay, well that's cool. But if you have a positive and a negative, then if the charges are the same, oh, that's going to be an attractive force. If you have two positives or two negatives, guess what? That's going to be a repulsive force. So not only do you have to worry about calculating the magnitude of the force, then you have to determine, well, which direction is that force going to act? Is it going to act as an attractive force, or is it going to act as a repulsive force? And this is why neutrons were so difficult to find, and actually to discover. We knew that neutrons were there because there was a certain amount of mass in the nucleus that we couldn't account for. But here's the problem with neutrons is that they don't interact with electric fields or magnetic fields. Okay? It's like, well, great, how we detect a neutron? It's like trying to find someone at a party who just, you know, is sitting in the corner and doesn't do anything. It's like, well, were they there? I don't know. They might have been, because they didn't interact. Now, you have Liza going, wah, okay, right? Hey, was Liza at the party? Oh, yeah, okay, right? You know, she was there. She was interacting with people, right? Hey, Liza was there. She's like the electron at the party. She's this sort of little thing, you know, running around, highly charged, you know, blah, 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 right? And you got, you know, Bruce, right, St. Bernard. He's just kind of chilled out with this positive charge, but we know he's there because we can see Elias kind of orbiting around him, right? Okay?
And he's just so tall.
And he's just so tall,
Everyone can see him.
right? So we have the proton and the electron, okay, right, kind of there, right? So, you know, and then we got Peyton, who's kind of the neutron, because he's there. He's just kind of chilling out, you know, okay? You know, he's an important part because he kind of stabilizes everything, right? But it would be hard to detect Peyton because of the fact that he's just not necessarily, he's going to be there, but he's not going to interact much. So here's the other thing in case you all haven't run into with the tape. The problem is it also interacts with your hands because your hands then are part of the system. Because I saw some of you when you were trying to bring it up here to the balloon and it would like peel back and it would attack your hands. So even if you look at what Henry Cavendish did, Henry Cavendish was the one that came up with the universal gravitational constant of 6.67 times 10 to the negative 11. So, and that was dealing with a gravitational interaction. So what he did is he was the one that had like the torsion wire and the spheres, and he brought them close and they measured the amount of torque it took. But he was so afraid that his mass was going to interfere with the system that he built a separate room onto his house that housed all the apparatus, because he didn't want to be a part of that system. So here's the problem with you all when you're trying to deal with charged objects, is because you also basically become a charged object. So when you were holding those pieces of tape and you were trying to see if they were interacting, some of you are going, and I could tell, and this is what I like about this lab from my perspective, you were getting frustrated. It was like, what's the right answer? It was like, I don't know. Okay? Right?
The thing is, you do know.
Oh, I do know. That isn't the issue.
We
Okay?
tried 3 different times to get 3 different answers.
That's just it. And so then you come up and say, well, we'll try it this way. And then I think Liza was you're the one that's like, I'm going to do this until I get somebody. That was Catherine. Okay, Catherine. It's like, I'm going to go around until I get the result that I want. Okay? And you eventually did you?
Thank you, Keegan.
Yeah.
Yeah.
You weren't
Okay.
talking him earlier.
He
Yeah,
screwed up
you
our
were.
live data and then he redeemed himself.
I did do it.
That's right.
Wait,
Keegan, I'm proud of you.
it
Thank
was
you.
not you.
Keegan.
So you screwed it up, but you think you redeemed it?
No, she fixed her tape and then it actually
No,
worked.
it was.
Okay.
Her tape just wasn't charged right. Yeah.
Okay.
They ripped it off.
Keegan
They ripped it off the
him.
pump.
Yeah. What a rip off. They ripped it off backwards instead of forwards.
Oh,
Okay.
what?
Elizabeth has
Upside
like,
down.
So basically what happened,
Not great.
and you wouldn't think Scotch tape would provide that difficult, but it is kind of cool at how it interacts. And you know, when you get it on the table, it's then, okay, you pull it off that way versus, hey, you stick it against each other and pull it off that way. You get completely different results. And so basically what happens is that tape acts, the glue side of it basically to a certain extent acts like a glue for electrons. And so when you pull that apart, okay, then you have an uneven distribution. But here's what's important. You still have the exact same number of charged particles. Okay, it's the exact same number of electrons, the exact same number of protons. You just have an uneven distribution of them. And so that's one of the things that I wanted you to see when you were drawing those diagrams. So if here's your piece of tape when it's like neutral, you have like alternating positive and negatives, okay? But then when you pull them apart, something had to change. Either you had a net gain of electrons from the other one with the same number of protons or the same number of positive charges, or you had a net loss of electrons and then that became positive. So one of the things that you have to understand is that you're not going to alter the number of positive charges because of the fact they're locked up in the nucleus. What you can change is where those electrons are distributed. So, on the lab, and I love grading these because it's always interesting to see like what you predict, and that's why I said don't be afraid to make predictions on this thing, because there isn't right or wrong. Okay, what is a right or wrong? Hey, you know, you said, hey, I think this is what's going to happen. So when you brought it up to the charged balloon, okay, clearly, and this is why I had you do the balloon part of it, because the balloon is negatively charged because it has an excess of electrons. So once you establish that as like the benchmark, and says, okay, now I know the balloon is negatively charged. Okay, great. Now I know the balloon is negatively charged. So when you bring that tape up there and that one repelled, then now you at least know which tape is negatively charged. Okay, because that's going to be repulsed. Now, and then you go into, okay, if the other tape is attracted to it, is that one also positively charged or is that just neutral? So that's why I had you take those tapes and go to another group to compare them. So let's say you think this tape is positively charged. Okay? So here's your scenarios. You think that one piece of tape is positively charged, okay? Because it was attracted to the negatively charged tape. You say, okay, it's positively charged. And that's a viable option, okay? Now, if you bring that to another piece of tape in a similar situation, and those two pieces of tape then repel each other, then you in effect know, hey, both of those are positively charged. Now, but if you take them and then you bring them near each other and they don't do anything, and there is no repulsion, that just means that these two pieces of tape were neutral, and that's why they were attracted to that negatively charged piece of tape. So that's why you have to set up the control. And so that's why it's so important on the attractive side to determine, is it actually attractive because it's oppositely charged, or is it attractive just because I'm inducing a charge on that other piece of tape? Okay? Cool with that. So it was, from my perspective, it was fun watching you all, because you all are used to clearly defined answers and, hey, you know, did X equal 5 or not? And you're going, well, this literally, that's the challenge of electricity. So that's why when Ben Franklin did his work, Ben Franklin had a 50-50 shot on calling the movement of the particles, were they positively charged or negatively charged. He guessed that it was positively charged particles that was moving. He had a 50-50 shot. He guessed wrong, okay?
How do we know that, like, what means that it's positive or negative? What side?
Once we get into, what do you mean, on the tape or what Ben
Yeah,
Franklin did?
why couldn't we just say that electrons are positive and call them that from now on?
Because.
Because that's not
We
what the
can't.
word means.
Yeah, because that, when Thomson found the particle, he got to pick and he said, oh, hey, I'm gonna make that
Oh,
negatively
okay, so
charged.
it is just one dude just decided,
Pretty much, yeah.
okay.
And Ben,
It just wasn't Ben Franklin because he didn't do it
well,
right.
well, Franklin did, he talked about positive and negative. Okay, he actually talked about like an overabundance of things. But the main thing is Franklin described a current of moving electricity as being moving of positive charges.
Yeah.
And that's what's gonna frustrate you all. I'm gonna tell you this right now. Once we start to draw like current diagrams, we're always gonna talk about as a positive charge that's moving. In reality, it's not. It's electrons, but you can argue that when an electron moves, it leaves a space where there's a positive charge that moves in the opposite direction. So schematically, you can make it work, but it really doesn't. Anyway.
Thanks. I hate it.
Anyway, sorry. Okay, so get those handed in then.
No.
Yes.
I've got my test correction. But I noticed something. I noticed something and I was a little bit curious. So, these two I got
What do I get?
wrong, but you understood them as
No, those are
Avoid
actually.
this, avoid this.
So it would be like,
Yeah, but
Yeah, it does.
if I do minus 2 and then correct that, I get extra.
anything over a
Thank you. Not a whole lot, but it's some.
Destiny's Child. Is that Destiny's Child by this trial?
Where are the scissors?
What?
Where do you need to?
Because I've got the frizzies.
And instead of singing, just say my name on it.
Just hold it and then start
I
carrying.
don't have one, I'm so sorry. No, you don't.
Thank you.
Right here, right here.
Just say my name.
Your babies are
Is that a grenade banana?
That's what I just.
Oh, yeah. Banana grenades? I love banana grenades.
Pull up the banana to people, they're coming to destroy.
What is
Oh boy, he's charging the balloon again.
I don't know the whole song.
Okay. So let's kind of go through some things. We'll start to talk about like the new equation. And so I just charged the balloon to make that negatively charged. So if I take a piece of plastic and rub it with silk, okay? And I bring that towards the balloon. So, using my magic wand, okay? So what can I conclude about the plastic? Negatively charged. So once we establish a benchmark and go, okay, hey, that's negatively charged, then that's something I can go with. So then if I take the silk though, and put it near it, then you can then that could argue that that's then being attracted, right? Because of the fact that if this became negatively charged, this had to become positively charged. Okay. So now we can take a piece of plastic. Okay. See that?
Whoa, it's also negative.
It's repelling.
That means
Okay.
What just happened?
So,
Z spin, that's the.
Oh my.
Well, it makes sense to
It's
flip
just
it.
the cloth. Oh, it's attractive, so it's.
we're just gonna, okay? So, the two pieces of plastic, you rub with silk, both became negatively charged. So now if we rub this, a glass rod, this is actually acrylic.
That's on wide too. Got it.
Oh, wow.
Woo!
That was strong.
Force is strong.
The force is strong with this one. So if I rub the acrylic one though,
Positive.
this became very positively charged, okay?
Bruh.
Now, here's the deal. Is there a chance that this is just, maybe just neutral, and it's just being attracted to it because it's neutral?
Maybe.
Yeah.
It's a possibility, right? So what could I do to kind of test that?
Test it with the plastic.
Test it with another one.
Well, I could test it with one that hasn't been
Charged.
Or
charged,
test the rag.
or test the rag. But the problem is the rag,
Oh.
well, the rag was all checked up from those other ones. But what I could do is I could test it against one that hasn't been charged. But just looking at it, based upon the amount of attraction that there is, you gotta kind of figure this is probably gonna be positive charge. Because even if I like put my hand here, okay?
Maybe more.
But the only way we could test it is to take a plastic rod and see. Now, let's say that the balloon is negatively charged, and it is. So, one of the things that you talk about doing is, let's say that we want to charge these metal spheres. So, if you look at them, number one, you get this nice kind of reflection that I can see all of you back there. So, what kind of mirror is it?
Convex.
It's convex mirror, right? Okay? And it's a pretty sharp curvature. So now, so even when I do this, right? All of you are right side up. Why?
Focal length.
The diverging mirror.
Yeah, it's a diverging mirror, right? So all of you are going to be upright. They're going to have a small image. So you all look pretty small back there, but I can see all of you, right? So here's the deal.
Now I know what it's like.
So let's say that I'm going to charge this rod. We've established that this is now negatively charged, right? Because it's going to repel that a little bit. Okay. So if this is negatively charged, and let's say that it has 4 units of negative charge on it, and let's say that this metal sphere is negative, or is neutral. So if I just bring this near this without touching, this is negatively charged, and I just bring it near it without touching it, what's going to happen, because this is a conductive sphere, okay, it's metal, it'll conduct this. So when I bring this negatively charged rod near it, what's going to happen?
It's going to become negatively charged.
Electrons are going to move to the other side, right? Chihuahuas are going, whoop, we're out of here, right? Lysas of the world are running over here. St. Bernards are left over here, right? But as soon as I take that away, what's going to happen?
Gonna go back to normal.
Yeah, because the Chihuahuas are going to go back, okay, we got this, we're cool, right? Let's go back, right? Now,
The lies is gaining sense.
if these are touching, okay, right? And I bring this near it without touching it, okay? So I've got a negatively charged here, right? So I touch these together, and then I bring this close. So then what's going to happen?
The electrons are
Right sphere is going to become negatively charged.
So this sphere over here is going to become
Negative.
negatively charged. This sphere over here is going to become
Positive.
Now, if they're still touching, when I take this away, what's going to happen?
They're just gonna go back to normal.
They're just going to be going
Spread
back
back
normal. But if I bring this near, okay, and I touch this, right? And then I separate them, then what's going to happen?
So one's gonna stay negative, the other's gonna stay
This one's going to be,
Negative.
this one's going to be positively charged. So the whole key to this is the sequence. So now, if I just bring this near, right, okay, nothing's going to happen. But if I touch them, and then bring this near, and then separate them, then I'm gonna have an unequal distribution of the charge. And this one would be negative of the charge, this one would be positive of the charge. But, what if I do this? What if I charge this, okay? Touch them, and then actually touch the spheres, and then separate them.
They're gonna both be negative.
Equal charge.
They're both going to be
Distribution.
negatively charged, and they're both gonna have,
Equal distribution?
yeah, so they're both gonna have half that charge, right? Because it's gonna, so here's what you can do. Depending upon what you wanna do, you can either make these spheres have equal and opposite charges, or you can have them have the same charge. But it all depends upon the sequence, okay?
So does that mean the rod also has the same charge as those two?
Yes, because then that rod's, it's gonna be equally distributed, so it'd be like a third, a third, and a third. Okay. So, sometimes you'll see this laid out like this, in terms of like a diagram. So you'll have like 3 objects, A, B, and C. And so initially, this really physically doesn't make much sense, but the idea makes sense. So initially, you're going to have sphere A, sphere B, sphere C. And let's say that A is initially neutral, B has a charge of a half, C has a charge of negative Q. Okay, so C is negatively charged, B has a half of a positive charge, and A is going to be neutral. So that's how everything is to begin with. So what we're going to do is we're going to touch A to B. Okay, so C has nothing to do with this. So imagine that I've got a third sphere in there. So A is neutral, B has this positive charge of 1/2, C has a charge of negative Q. Okay? So I'm going to touch A and B together. C has nothing to do with this. Okay? So if I touch A to B, how much charge is going to be on each one?
1/4.
1/4, which is going to be half of this, right? So you'd have Q over 4, Q over 4, and
Negative.
now, when I add all of them up, okay, what's the overall charge of the system?
Maybe 1/2 negative.
Yeah, negative Q over 2, negative 1/2 Q, right? So when this gets done, then everything still has to add up to the same amount because charge has to be conserved. So now, what's another thing that I could do? Well, I could touch B to C. So A is done, right? Because A is now separated out. So that's going to be Q over 4. So if I touch B to C, now I've got Q over 4 and negative Q. So how much charge is going to be on each one?
Negative Q over 2.
So I've heard negative Q over 2.
Wait,
Point.
Katie,
Yeah, it
what'd you
would
say?
Negative 3/8, yeah.
That's what I was thinking.
Negative 3/8 Q.
negative Q over 4 is what I meant to say.
Negative Q over 4. Okay.
I'm in the negative 3.
I'm gonna make grades too.
Yep.
I'm on that train.
You're on the negative 3/8 train. Why? You should be.
Because you add the Q over 4 and the negative Q, which would be negative 3. Yeah, 3/4. And then you divide that by 2, which would give you 2
Negative
negative
3/8.
3/8.
That makes more sense.
Okay, so here's all I want you to get out of this, is that no matter what, when you have spheres that are charged and they interact, you're going to split that charge between the two, because that's easiest for Mother Nature to do, and Mother Nature is a lazy prima donna. So Mother Nature is always going to take that opportunity to just, it's kind of the Bernie Sanders thing, we're going to spread the wealth. Okay,
No, it's the Thanos thing, perfectly balanced.
okay, well, let's go with politics. Okay. All right. Now, here's the next big equation. This is going to be our bread and butter for a while.
Oh, delicious.
Is this the greatest thing since sliced butter?
No.
What?
Is it a 3 or a 9?
9.
Where'd you get a 3 from?
Oh, no, it's 10 to the, is that 10 to the 3rd or 10 to the 9th?
It looks like a 9.
So bad.
Oh, yeah, I can see
It's
it.
a
I
3.
understand.
I can see it.
I thought you meant the
This
first
Keystonian
line.
physics you're doing right now.
This
This
number.
is what I keep doing.
Oh, wait. No,
That's
I
K.
know. That's K, okay, I was confused. So it's confusion. It's fine now.
Confucius say shush.
Not that we.
Okay. So first off, we're going to kind of begin to look at this idea of concession. So all this equation is F equals K Q1 Q2 over distance squared. So what this does is it gives you the electrostatic force between two charged particles. Now, this value of K is 9.0 times 10 to the 9th. Your book, or on your equation sheet, and I don't know why, they're just trying to be weird, they list it as 1 over 4 pi epsilon naught, okay? And if you find epsilon naught, which is like the vacuum permittivity constant, and you multiply that by 4 pi, and you take the inverse of it, you get 9 times 10 to the 9th, okay? So, and your book is weirder, because your book listed as like 8.99 times 10 to the 9th, okay? You just cut through all of it and just use 9 times 10 to the 9th, okay? Now, just like the universal gravitational constant is like, 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared, because the units work out. The same thing is true of this electrostatic constant. So your Q's are going to be your charge, which are going to be in coulombs, and then you have a distance, which is going to be in meters. So with this one, this is why it has the units that it does, because you've got coulombs up here, squared. So that'll drop out the coulombs. You're dividing it by meters squared down here. That cancels that out, boom, you get newtons, okay? Now, just like a gravitational force, if you have two massive objects, okay, those two massive objects that are very, very close together are going to have a strong gravitational pull, because you have large masses and they're very close together. Now, in contrast to that, you have a proton on one side of the universe and a proton on the other side of the universe separated by light years. Guess what? There's not going to be much of an attractive force between them because they are so far apart. So, what's going to happen here is that you can calculate this force, but here's what's going to be different than a gravitational force. It could be attractive or it could be repulsive depending upon the situation. Okay, so that's the other thing that you have to watch. So like when I was doing this with the balloon, okay, and I was trying to calculate that force, well, depending on what I put up there, it was either going to make that balloon accelerate towards that object, or it was going to make it repel by that object. Now, here's an interesting thing that happens. It's like gravity. So let's say that you have your charges, and your charges are fixed values. The only thing you can really manipulate is the distance. So you have two balloons that are charged, and you bring them close together. And then this is what I showed you with the carts. When I had the two balloons, we pushed them together, and we let go, and they began to drift apart. Well, when that happens, as those balloons or those charged particles begin to drift apart, what's going to happen to the value of that force between them? That force is going to become smaller and smaller and smaller because you're increasing the distance more and more and more. Okay? So as the force becomes less and less and less, what's going to happen to the acceleration of the particles?
Less and less and less.
Yeah, it's going to become smaller and smaller and smaller. So your maximum acceleration is going to occur when those particles are close together. Because after they begin to drift apart, the force is going to become smaller, the acceleration is going to become smaller, until eventually it effectively will reach a point of constant velocity because your acceleration is going to become such a small value. So that's something to think about. Now, let's say that I've got two charged particles here, okay? Each has a charge of 10 nanocoulombs, and I'm going to have a charged particle, let's say that's a positive third in the middle, okay? So one of the things that we'll talk about, just like in terms of net forces, okay? You know, what we paid off the gravity mafia, or we paid off the friction mafia, the same thing's going to happen here.
So do you have another mafia then?
No, well, this is kind of the electrical mafia, kind of, okay?
The electric company.
Yeah, the otherwise known as Evergreen.
This one is not a mafia, it's a legitimate business.
Well, this is why I like my solar.
You say
Only
legitimate.
problem is my solar panels are now like covered
Legitimate.
with snow and they're not working. Anyway,
It really is a mafia.
Two
Secret.
Huh?
no, I'd say after school, I'm
You
gonna
just
have to
need
go out.
massive
Do you
wind.
need help?
You just need massive windshield wipers on.
No. If you want to go after school and help me, like, we don't have to sweep them all, we don't have to get them all off, but if it's quit snowing, it's cool because you just have to like clear off kind of like the bottom foot, and then that section then starts to work, and then as that section works, it warms up, and then it melts the panels as it goes. So,
Like when you turn on
but you're not at all dressed.
Oh, no, well, I had a 25-minute snowball fight in AP Chem. We got done with our, we got done with our notes, and then we went outside, and all the teachers were out there, and we were just like,
Can we do that?
it was crazy.
after school.
Can you be a potato?
Okay, anyway,
No, but I can be 50 to 60% of a banana.
okay, so here's the deal. So, let's say, and on Tuesday, God, it seems so we were going to go 5 days without class, okay? So on Tuesday, you'll also see how this is going to be affected by electric fields. So right now, we're just going to talk about forces. So, if I've got a 10 nanocoulomb charge here, and I've got another positively charged particle here, and then a 10 nanocoulomb charge, what we want to look at is what's going to happen to the net charge on that center particle. So what you want to do in this situation is kind of like two anti-gravity planets, and you're going to have another planet in the middle. So don't worry about this side for now. You got this 10 nanocoulomb, and I don't care what this charge is. It's just a positive charge. Don't worry about it. It's just a positive charge, and it's separated by 2 centimeters. So what's going to be the force on this one? And excuse me, which direction is the force going to act on this particle based upon the one on the left? What's it going to try and do? It's going to try and repel it and push it to the right. Now, if this one, because it's the exact same distance away, is also positively charged, and this is positively charged, what's going to happen?
It's gonna.
It's going to try and push it that way, right?
So-
So as long as those two forces are the same, this is going to feel force, a repulsive force from both sides, but what's going to be the net effective force? 0, because they're going to cancel each other out. Just like if you had two negatively charged particles out here, then instead of being crushed,